Now that we've learned about a variety of functional groups and we've seen the wide variety of types of organic compounds, our next focus will be on physical properties of organic compounds. So we're going to talk about some examples of physical properties, then look at the intermolecular forces that are responsible for those physical properties, and then we'll look at comparing and predicting physical properties in different compounds. So in this video, we're focusing on physical properties themselves. Some examples of physical properties include melting point, boiling point, and solubility. There are a number of other physical properties we could consider, but these will be our main focus, both in lecture and in lab. Let's start by looking at some of the simplest organic molecules, which would be the alkanes. This is methane, which has only one carbon, ethane, an alkane with 2 carbons, and propane, an alkane with 3 carbons. And let's consider the boiling points of these compounds. So the boiling point of methane is negative 160 degrees Celsius. For ethane, it is negative 89 degrees Celsius. And for propane, it is negative 49 degrees Celsius. So all of these compounds boil well below room temperature, which means they're all going to exist as gases at room temperature. But even though they're similar to each other, they're all alkanes, the only difference is size, somehow this still leads to a significant difference in boiling points. Here's another set of compounds, and this time we're comparing propane, which is an alkane, with dimethyl ether, which has an ether functional group, and ethanol, which has an alcohol functional group. Now, these are dissimilar to each other, but they are similar in terms of molecular weight. Propane has a molecular weight of 44 grams per mole, and these two compounds are 46 grams per mole. So very similar in molecular weight, but if we consider the boiling point, we already said propane has a boiling point of negative 49 degrees Celsius. Dimethyl ether is negative 24 degrees Celsius, and ethanol has a boiling point of 78 degrees Celsius. So whether we're looking at compounds that are similar to each other yet differ in size, or compounds that are similar in size but otherwise dissimilar from each other, we see that there is a significant difference in boiling point. We will also see differences in other physical properties as well. And the reason has to do with differences in intermolecular forces. Intermolecular forces. So these are the forces between molecules. So not what's within the molecule, because those would be our covalent bonds, but we want to consider the intermolecular forces that are between one molecule of propane and another molecule of propane, for example. As we think about physical properties, we want to think about changes of state between the different states of matter. So we want to consider solid, liquid, and gas. And I'm just going to use a little circle to represent a molecule. So in a solid, we have our molecules very close to each other, and they are very organized. So we have intermolecular forces that are holding these molecules together with each other. So let's say that this represents intermolecular forces between the molecules. In a solid, we have intermolecular forces and they are highly organized. In a liquid, we still have our molecules very close to each other, but they're not very organized. So we still have our intermolecular forces, but they are less organized. Now in a gas, we might have one molecule here, another molecule here, and another molecule here. These molecules are now so far apart from each other. They're not together and organized. They're not together and disorganized. They are far removed from each other. So there are no more intermolecular forces. So as we think about changes of state, if we're going from a solid to a liquid, we're talking about melting. And as we are melting, to think about it in terms of intermolecular forces, we're going from highly organized intermolecular forces to less organized intermolecular forces. But as we go from a liquid to a gas, this is where we think about boiling. And in the case of boiling, we go from having molecules that are held with other molecules by intermolecular forces to molecules that have no intermolecular forces. So I like to focus on boiling point because this is where we have the most drastic change. So we're going to focus on boiling and the boiling point because this is where we break all of the intermolecular forces. Keep in mind, when we're talking about boiling, we are not breaking bonds. We are not breaking covalent bonds. We are breaking intermolecular forces. Now, to break these intermolecular forces, it takes a certain amount of energy. How much energy depends on the strength of these intermolecular forces. The stronger the intermolecular forces, the more energy is required, therefore the higher boiling point. So, as the strength of the intermolecular forces increases, the boiling point will increase because stronger intermolecular forces take more energy, a higher temperature, to be able to break those intermolecular forces. Another important physical property would be solubility. So we would have to think about solubility in a particular type of solvent. So we could consider water solubility or solubility in a nonpolar solvent such as hexanes, for example. As we're thinking about solubility, what we're really thinking of is an exchange of intermolecular forces. We have an exchange of intermolecular forces. Let's say we have a sample of one compound and it has a particular set of intermolecular forces. And we also have another sample of a different compound, and this one has different intermolecular forces. So we can physically force them together by shaking them up, but then the question is, will they remain mixed or will they separate out again? So what we're really asking is whether they will give up their particular intermolecular forces to be able to instead accept intermolecular forces among the different types of molecules. So do the circles want to stay together, or are the circles okay intermingled with the rectangles? Well, it depends on the type of intermolecular force. And what we always want to keep in mind is like dissolves like. In other words, if these two compounds have similar intermolecular forces, then they will exchange these intermolecular forces and these intermolecular forces for new intermolecular forces between all of the molecules. This only works then if the red and the green are very similar intermolecular forces. On the other hand, if these are held together by a very strong type of intermolecular force, and these are held together by weak intermolecular forces, then the best they can do as a mixture would be the weak intermolecular forces. So in this case, the circles don't want to give up their very strong intermolecular forces to have to settle for weak intermolecular forces. So while you can shake up the two samples, mix them together, physically force them to mingle, but then give it a little time and they will separate back out so that these will form their intermolecular forces between each other These form their intermolecular forces between each other, and there is a separation between them. So we can consider melting point and boiling point, and we need to remember that the stronger the intermolecular forces, the higher the melting point or the higher the boiling point. As we think about solubility, we need to think about the exchange of intermolecular forces and will two different compounds exchange intermolecular forces to be able to interact with each other. So the strength and type of intermolecular forces will have a direct impact on melting point, boiling point, and solubility.